Será?
Tá com sono.
Então, não sei. Pode continuar.
Okay. So I can express B in terms of the Bogoliubov coefficients, and if the vacuum 0 is the vacuum of my U basis, so I have this U chi stars, and we have the vacuum 0 defined in terms of this basis. That's just the vacuum where the coefficient A are going to annihilate. So if I apply this coefficient B here of this expansion on this vacuum, what we're going to see is that this part here, this coefficient A here, are going to annihilate this vacuum, but the second coefficient here are not going to annihilate the vacuum, because this is A dagger acting on 0 are going to just return the state of one particle. So the only possibility that the coefficients, the vacuums are going to be equivalent is that if my coefficient beta are going to be 0. Because if the coefficient beta is 0, so the B coefficient acting in 0 are going to return 0. But only under this condition. If not, if this not happen, then the coefficient B will not annihilate the zero vacuum. So but it annihilates the vacuum of the bar vacuum. That's the vacuum of this base, because this is the definition of the vacuum on this basis. So in general, we need to have a Bogoliubov coefficient equal to 0 in order to obtain in order to have both vacuums to be equivalent. And this is more explicit if we write down our number operator. So I can define basically this number operator accounts for the number of particles in my system, and it's defined as this product here. So since I have two bases, I have two definitions of the number operator. I have one definition in my U basis and one definition in my U bar basis. So the question is, if both vacuums are different, so I can compute the average value of the number operator defined in the U bar, acting on my original basis. So these expressions are not 0, but actually it depends on the square modulus of beta. This means that the vacuum, the 0 vacuum, that's the vacuum of my original basis, is not return 0 particles in my U bar basis. Instead, it will return a different number. That's a non-zero number, which means that the state of 0 particles in my original basis is filled with particles in my second basis. So in principle, the definition of particles and the number of particles explicitly depends on the basis we use in order to expand our field. If we consider one basis, we have a definition of some number of particles, but if if we use another basis, we will have a different number of particles. And the only condition that we will link the different bases is that if the Bogoliubov coefficient is 0. So if I have two Lorentz observers, for example, and they are connected by Lorentz transformations, and I can show that two different inertial observers, they have the same notion of vacuum and the same notion of particles, because in case of Lorentz transformations, the Bogoliubov coefficient is necessarily 0. So it's a very good thing, because the experiments that I'm going to do in my laboratory are the results I'm going to make in my laboratory are going to be the same results that you probably are going to observe in your laboratory. There are not different numbers of particles that will be observed. Okay, but if we consider different, instead of connected two observers by Lorentz transformations, we connect two observers by Hinder transformations, for example. That's basically the transformations that link an inertial observer with a uniformly accelerated observer. So I will have two expansions of my field, two different expansions, the same Klein-Gordon field. I can expand in a Minkowski basis, and I can expand in this bar here, in a Hinder basis. So by computing the Bogoliubov coefficients, those coefficients are not so easy to compute. They are very complicated, actually. There's a lot of complex integrals and complex analysis that you need to make to compute the Klein-Gordon product. But in general, we can show that the number of particles of in Hinder space, let me rephrase that. The vacuum of the Minkowski space are not a state of 0 particles in Hinder coordinates, but actually it corresponds to a Bose-Einstein condensate with temperature that's proportional to the acceleration. Just computing the average of the number operator. This is called the Unruh effect. And what is nice to observe is that the same idea of change the basis is we can use to study particle production. Here, the different bases arises from the change of referential. So I'm change the referential, I'm change my coordinates. So I have two different definitions of vacuum. But if I consider expand the universe, for example, I can observe a similar effect in two different times. So the idea to generalize the Klein-Gordon Lagrangian to the case of a curved space-times, the generic metric G. In order to do that, we need to replace the Minkowski metric by the metric G, and we need to replace the ordinary derivatives by covariant derivatives, and we need to replace the volume element, that's this here in Minkowski space, to the covariant volume element, that there's this square root of the determinant of the metric here. G is the determinant of the metric. And we need to define a Klein-Gordon inner product in curved space-times. So this here is just the definition of my inner product in curved space-times. So here I have the covariant derivatives instead of the ordinary derivatives. I have this is called of Cauchy per surface. I will not go into details on that. But if we consider Sorry. Okay. So once we make all those changes I listed before, I can write down my action in a curved space time. So I have here the determinant of the metric, the covariant derivatives, and I consider here additionally a coupling between the scalar field and the space-time metric, a non-trivial coupling, because we have a coupling here, some kind of coupling, because of this, the metric with my scalar fields. I have the metric, determinant of the metric here. So in some sense, I have my fields in the background is interacting in some sense with the fields. But I also consider an explicit coupling between the scalar field and the metric, where this quantity here is just the heat scalar. So this psi here is just a number that is called non-minimal coupling. C is equal to 1/6 is just called in the literature of conformal coupling. Psi is equal to 0. It's just the minimal scenario, so I do not have this interaction here. But in order to address this is actually a little complicated. We make some change of variables. So, all right. Before of everything, we are going to consider the metric of Friedemann, Lemaitre, Robert Wilson metric. That's just the metric of the expanding universe. And we, instead of use the usual time t, we are going to write our action in terms of our conformal time. And we are going to introduce auxiliary field just in order to take the expansion factor that appears in multiplying our field. By doing this substitution, my original action obtains this expression here. That's just very similar to the Klein-Gordon action in Minkowski space. I have this prime here denotes a time derivative, prime just a time derivative in order to conformal time. I have this special derivative. So, and I have a mass term here. But the difference is that the mass here is dynamic, in the sense that depends on the time. So actually, the expression of this effective mass here can be written in terms of the original mass plus this term that depends explicitly of gravity. And this time dependence of the mass of that appears in my action actually is the responsible to bring the creation of particles. So the recipe is the same. We are going to extremize our action and obtain our equations of motion are just Klein-Gordon equations, similar to Klein-Gordon equations, but with this effective mass here, with this effective mass that depends on the time. And we will expand the expression in terms of the Fourier modes. And once we put this expansion in terms of the Fourier modes in my equations of motion, I will obtain the equations of motion in the K space. That's very lot easier to solve than the original space. So this space here, sorry, this equation is just the usual quantum harmonic oscillator equation, but the difference is that on the frequency, that in this case depends on the time. So that's a very good thing to do for those that are doing scientific initiation, is that we can study the particle creation from the study of the harmonic oscillators. But instead of consider the usual harmonic oscillator, you just need to consider the a time-independent frequency, or maybe a external force acting on your harmonic oscillator. And this will lead us to very similar results of the particle creations in cosmology. So once again, this frequency here depends on the mass. On the Clay-Gordon case, it's just k squared plus m squared. But here it's the same, but instead of m, we have the effective mass. That depends on gravity. Depends on the heat scalar. So the main idea here is to solve this equation and expand in terms of positive and negative frequency modes. But sometimes this time dependency here is so complicated that we are not able to solve and obtain this explicit decomposition in terms of Fourier modes. So this is what I said. What we can do here is to consider asymptotically flat three-dimensional Robert-Walker metric, in such sense that we are assuming a scale factor A that such that when eta goes to minus or plus infinity, the metric of my space-time are going to just be the Minkowski metric. I can achieve that by assuming a conform factor, so expansion factor, just something like that. A plus B hyperbolic tangent of whole eta. If I consider this expansion factor just as this expression, I can achieve those limits here. I mean, this is not usually the usual cosmology scenario, but I mean, we can play with this expansion just to obtain those asymptotically flat space-times. So, since we have asymptotically flat, I mean that in these limits of n of eta going to minus infinity and plus infinity, we are just going to have the Klein-Gordon action. So I can have my frequency here, that's time dependence. In this limit, it will be a constant. I call it of omega in, and here's plus infinity. I have another constant that are not necessarily the same. So we can expand our field for two different moments of time. Initially, we are going to have just the quantum harmonic oscillator equation, but for this frequency here, omega in, and late time we are going to have the same equation but with another frequency, omega out. And as a consequence, my psi here, psi kappa, that the coefficients of the Fourier expansion are going to be different. They're going to have the coefficients in and coefficients out. So despite being very similar, those fields have different expansions. And we can relate those different expansions through the Bogoliubov transformations. So if we consider, if there is different expansions, so in principle, the notion of vacuum will change with time, because in the beginning I have an expansion, in the end I have another type of expansion. So my vacuum in the beginning are not necessarily are going to be the same vacuum in my final state. Some kind of that, but it's to have this transition, you have to give the explicit dependency in the intermediate interval. But we are just assuming asymptotically flat space-time. But we have Minkowski in the beginning, Minkowski in the end, but because in the middle you will not have Minkowski, the vacuum notion are going to be different. We're going to have a vacuum in the beginning and a vacuum in the end.
What does this flat space go into a different flat space and then going back and again?
Sorry.
Why this change to a non-flat and then again go back to a flat space?
Oh, it's just a toy model. I consider this.
But is there any reason, to assume this toy model?
And I'm just assuming to didactical purpose to show that even if you have Minkowski and Minkowski, because in the middle you have something different,
Okay.
but the usually what we do is to study the start from a inflationary cosmology and go to a Maia dominance, because right after the inflation we have a brief time of Maia dominance, and then we have the usual hot Big Bang theory. That's the usual approach that we need to take in order to study particle production. I'm just make a simple introduction, but since we have two different expansions and two different notions of vacuum, so the number of particles, the vacuum in the beginning, the zero in vacuum, are not going to be the state of zero particles in the end. Actually, it's going to be a state filled of particles, and this exact expression, this is actual dependence will have to be with this beta coefficient of the Bogoliubov transformation. So if the beta coefficient is 0, then we have the same vacuum. If beta is not 0, the vacuum are different.
Okay, this beta in the Bogoliubov transformation is related to it's just one of the coefficients.
It's just one of the coefficients. Yeah.
So what's the role that the other one plays?
The alpha coefficient. I don't know if it has a particular role in the theory, because because the key point here is that the positive and negative modes in the end could be expressed as a mixture of positive and negative frequency solutions of the beginning.
Okay.
So the beta coefficient that plays this role to make this mixture.
Okay, so can you go back to this one?
Here?
Yes.
Bogoliubov are here.
Okay. So you somehow parameterize the chi out with the chi conjugated, and then you can just assume there is only one coefficient, or the other one just appear because of the scalar product also.
Yeah. Because of that, they are not important, because the scalar product will kill the alpha coefficient. Just to remind, the beta coefficients just what's going to be left of the scalar the inner product.
Okay.
So in the case that the of expansion factor, just like this expression was a hyperbolic tangent, it's possible to show that the beta coefficient this expression here. It's really hard to compute these Bogoliubov coefficients once they are not 0, because there's a lot of complex analysis that we need to do. But the main point is that we have different for this case of Minkowski something, and after Minkowski we have the number of particles are not going to be are going to change, are not going to be the same. So it's some kind of cosmological particle production just because of the expansion. Even if I consider my initial coupling in terms of psi, phi square, and the heat scalar as 0, this will happen.
But in this case, I'm just producing some type of scalar point.
Yeah.
don't know, for example, like the mass. You don't have any. But you don't have any. I mean, do you know the properties of the internal properties of the field?
I mean, there is, if you consider.
Or you just know about the fluid, the behavior, the cosmological behavior.
No, if you consider the cosmological behavior, the expansion and the inflation and some, you can put some limits on the masses.
So, for example, so from this expression, from this sparkle that they are producing now, we have some kind of potential for them.
Dark matter, you say?
No, I mean, for example, if I have inflation in an inflaton field, I have a potential. Even if this guy behaves differently, cosmologically speaking, it will have a different potential.
Yeah.
So in this case, and you say, let's say we have now, just putting some context. So we have this transition and reheating. Then we have now, due to this, I don't know, some kind of curvature difference during the expansion of the universe, we have this production of particles.
Mm-hmm.
So how do we know the potential? How do we know the Lagrangian of these particles that were produced? Because to me, if these particles are not in my Lagrangian, see, they do not exist. If I am producing them, it's because they exist in my theory. That's what I mean. So I expect that they are the particles that are started in the beginning.
Yeah.
So it is like some kind of resonance production, or I mean, you have for example, when you have the super radiance, you have a lot of bosonic particles, and the number of particles start to increase due to some kind of oscillations, blah blah, due to the gravitational field, blah blah. So in this case, you would have similar things. So you don't have a new species. You have a new species. You just have the same particle, but now the number is bigger.
I mean, the same particle I mean, assume an expectation field phi, and it will be produced particles of this phi. Okay. After the particles that are produced can decay in some other different particles, but I mean.
So it will be regardless the potential.
Yeah. But the potential that you use to inflation will change some of the properties of the mass of the possible particles. Yeah, but I mean, this happens in. This is a very simple scenario, but in the case of the inflation, you can put some limits on the mass, and this is people are studying this a lot because they are assuming that it could be some explanation of dark matter, for example. Because I mean, it's not. It's just produced gravitationally. So I mean, you do not need to interact with other particles and so on. So I mean, I was in a lecture of Kobe once. I took some lectures of him, and I mean, he was saying that he's not believe in any of this collider, this
signatures.
Yeah, of dark matter because they are produced just gravitationally.
Yeah, some people do that.
Yeah.
But it's true. I mean, the feeling that I have is some kind of this, but at the same time, I think there is another interaction playing.
Yeah.
So it's kind of, but most people now, not most people, but many people are going to this direction, especially because it's easier to think, because we just have evidence from gravitational. Physics, let's say, but yeah, yes.
I mean, I just took the scalar case, but we can consider fermions, we can consider vectors, even spin 2. and this is also possible. So just to finish, the cosmological particle production results from the behavior of the quantum fields as in a time-dependent background. And in a flat space-time, there is a natural choice of positive frequency modes and negative frequency modes from which we can expand our field. But in curved space-times, this is not also true. In the particular case of the asymptotically flat space-times, we have that the notion of positive and negative frequency modes are preserved in the limits of the conformal time. It goes to minus and plus infinity. However, the departure from the Minkowski space at the intermediary stage leads to a mixture of positive and negative frequency modes that can be translated into Bogoliubov transformations, and as a consequence, the vacuum of in the beginning and in the end are going to be different. So this is just the basis of the cosmological gravitational production. If I want to study more and to be more precise, to make some research on that, I need to consider specific models of inflation and consider the transition from. They say that in the transition from in the end of the inflation, in the written error, there's a lot of this particle production that can be very rich candidates to dark matter. So it's a very interesting topic to study. And the key point is that the time dependence is induced by. The time dependence induced by cosmological evolution that is going to make this cosmological particle production to occur. Just the expansion of the universe. So it's I think that's very elegant formally. But as I said, to make research, you need to the inflation and the transition from the heating, and after for the hot Big Bang cosmology. So the notion of vacuums, they are different, but it's that's the basic of the story. So it's just that. I think I can change here, can end here.
Today we will not present more thoughts because there is just 4, and Victor will spend like 40 minutes. So
okay.
We are out of time, so I can present next week.
Okay.
40 minutes. 40 minutes. 40 minutes.
What presentation? Probably, I don't know.
Okay.
I didn't present it yet, so I have no idea.
Matheus did a class now. Lecture.
Okay, thank you so much, everyone, to attend this class. See you next time, next Friday. Bye-bye.
Now,